You don't need explosives if the speed of the projectile and its kinetic energy is higher than the energy that would be in the explosive shell itself. So it was a fascinating calculation to make. So here it is. So I have this delivery system with a warhead, and I put some bomb device in the warhead, and you can calculate how much energy that is. Then I send it, and it hits, and it blows something up. But suppose I send this thing really, really fast. Really, really, really fast. I can calculate how much kinetic energy this thing has. There will be a point where I give it so much kinetic energy, the kinetic energy is greater than the chemical energy of the conventional explosive that I put in the warhead.
Like Shoemaker Levy.
Well, for example.
Yeah.
No, I give you a terrestrial example. Right?
Okay.
It's what you would call a high-speed collision. This is more than you bargained for in our time together, but I will tell you.
No,
okay, you ready?
Perfect.
The argument for the longest time that the craters on the moon were calderas from volcanoes and not asteroid impacts. The geologists argue strenuously these can't be asteroid impacts. They've got to be calderas. These 1,000 craters on the moon. Why? Because everyone is a perfect circle. And if asteroids are coming from space, they would come from all angles. And if you come in at a shallow angle, you get an oval. And even shallower would be more ovals. So you'd have a whole range of circles and ovals and ellipses. And you don't see that. They must be calderas. It was not
Explain
until...
a caldera. It's a volcano.
Oh, it's just a volcanic...
And it leads a crater.
Volcanic crater. That's all
Like
it is.
Yellowstone.
Yeah. It's a volcanic crater. That's all. And it's a little more poetic, a caldera.
Right.
But it's a crater left by a volcano that has exploded.
Like the boom was so big, the mountain's gone, and now it's just a big hole.
Or at the top of the mountain, there's a crater at the top of the mountain, like Crater Lake. That's a round hole in the top of a mountain. Was that once a volcano? I don't know, but it's a hole. Okay. So in the 1970s, we were able to do calculations with high-speed computers, with good computers, and what we found was if the object is moving faster, if the kinetic energy of the object is higher than the energy that's holding the thing together, okay? So what's holding together a rock? The chemical connections of the silicon and the oxygen and everything, and the iron, everything that's making the rock is holding it together. You can calculate how much energy is holding it together.
And if it's going 45,000 miles
So
an hour.
write down that number. Now I send in the asteroid with a kinetic energy higher than the energy that's holding it together. On impact, it explodes. Because all that energy goes back into the rock because the thing isn't moving anymore. Where did the kinetic energy go? It digs a crater, number one, by virtue of putting all that energy back into the stone, and that explodes it. So on impact, even at an angle, it is a singular point explosion. And that's why every single crater is a perfect circle. We call that a high-speed impact, where the speed is greater, the energy of the speed is greater than the energy that's holding it together.
That's amazing.
Now, you have experience in this, okay? Have you ever thrown do this next, we're in California, sorry.
Snowballs?
Snowballs. Take a snowball.
Go to Big Bear. They have
Take a
snowballs up
snowball
there.
and face a barn wall and throw the snowball at it. And it'll make a little circular mark on it. Now change your angle to the wall and throw the snowball again. It'll still make a small round mark. And it'll keep doing it. You know why? Because the speed with which you threw the snowball, that energy is greater than the energy that's holding the snowball together. Because hardly any energy is holding the snowball together. It's just loosely packed snow. So when you do it against the wall, you see the snowball completely disappear in a mini snowball explosion, if you will. So this works for any comparison of projectile speed and what we call the binding energy of the object itself. This is why the intercontinental ballistic missiles never carry conventional warheads, because their speed coming out of space, because they leave the atmosphere, go from one continent to the other, then they fall out of the sky. That speed gives them more kinetic energy than any conventional warhead would have had.
Whoa.
But then we figured out how to make small nuclear warheads. The nukes. Now you're talking energy. The kinetic energy of the ICBM is not higher than the nuclear warhead that we now put in. That's why all ICBMs are nukes.
Wow.
The V-2 rocket basically didn't need an explosive warhead in its tip. It came out of the sky going 5 miles per second. There was none of this. That implies you're hearing the thing. It's coming in supersonically.
Whoa.
You're sitting there at a cocktail table on a block, and then the block is obliterated in the next instant. You didn't even know to look up.
Wow.
So that's and they added explosive anyway, but they probably didn't need to.
Now, to go back to Shoemaker-Levy, there was a comet that slammed into Jupiter. Now, Jupiter's a gas giant.
Yes.
I've always been confused as to what that means.
Oh, most of its mass is in the form of gas.
Most of its mass.
Oh yeah, 90-something% of it is. Yeah.
So when Shoemaker-Levy slammed into Jupiter and
It
made
was
an
going so
explosion,
fast, the gaseous atmosphere was like hitting a brick wall.
whoa.
That's how fast it was moving.
So that's why the explosion was
Oh,
bigger than Earth.
that's exactly. So it slowed all of its kinetic energy that it had got put back into the object itself because it slowed down very quickly relative to its speed, relative to the. So here's this comet. I forgot how big Shoemaker-Levy was. So now it goes into the atmosphere, and you say, well, isn't it just clouds? And it could. Watch how fast it's going. You can ask the question, over how much distance will it plow through its own mass worth of gas? That's a question, right?
Right.
That has to plow that much mass out of the way. That's an
Right.
important resistive force, right?
Yeah.
So how much atmosphere? So that's a lot of atmosphere because it's gas and this thing is solid. However, the thing is going, 15, 20 miles per second? It's falling into Jupiter at 20 miles, whatever the speed was. If you go at 20 miles per second, you will cover that much atmosphere in a fraction of a second. So in a fraction of a second, you go from 20 miles per second to 0, or a tiny fraction of that speed. All that energy has to go somewhere. It goes back into the system. It's a comet made of ice. Ice is not held together very easily. The whole thing explodes on impact.
That was another terrifying statistic that I read about the impact that hit the Yucatan and killed the dinosaurs. That how deep it had gone into the Earth's surface within the first second.
Oh yeah. These are numbers that are staggering once you calculate what they are. And like I said, if you come in fast enough, Earth's atmosphere is might as well be a brick wall to you. And by the way, you go 60 miles an hour down the road, roll down the window, just stick your hand out the window.
Yeah.
You have to use muscle energy to not have your hand blown backwards against 60 miles an hour.
Yeah.
Of air against your open palm. Just try that next time. See what kind of energy that requires. And that's 60 miles an hour. Now imagine 5 miles per second, 10 miles per second, 20 miles per second. You're toast.
How deep did the asteroid that hit and killed the dinosaurs, how deep did that thing go in the
Oh,
first
so
second?
what was that? That was a 150-mile diameter crater, something like that. I forgot the exact numbers. So there's a relationship between the depth of a crater and the diameter and the mass of the thing. So no, it was miles down. I mean, it's
Miles.
Oh yeah. Well, let me think.
And Earth rang for like a
No,
million years.
what happens is, let me take that back. I don't know if it's miles. It's
I think it was what I read. I don't remember the exact statistics. Well,
excuse me. No, it's got to go miles down because the thing is miles. The asteroid itself was the size of Mount Everest. So the asteroid itself is like 5 miles across. So it's deep. No, you just don't mess with this. By the way, the crater in Arizona, called Meteor Crater for obvious reasons, that can sink a 60-story building. And that's not even a mile across. And now we're talking about a crater more than 100 miles across that took out the dinosaurs.
that famous one in Arizona could sink a 60-story building?
If you put dirt up to the rim of that crater, you can bury a 60-story
Wasn't
building.
that an instance where this is your whole calculation about explosions and about the amount of energy, that they were looking for raw materials that caused that crater. Because they
Correct.
thought that they could mine it.
Correct. They first thought it was volcanic, and the geologist thought it was volcanic again. But one geologist in particular, Eugene Shoemaker, who was in line to be on one of the lunar missions, and then he had like a heart murmur, and then they sent Jack Schmitt in his stead, who was also a geologist turned U.S. Senator from Arizona? Who was he senator from? I forgot. But can you look at Jack Schmitt, where he was senator from? Forgive me for forgetting, because I'm friends with him, so I should have known.
Yes.
Jack Schmitt, SCHMITT. There's no D in it. But
Mexico.
Yeah, so I was right. So it's New Mexico. Oh, I said Arizona, so New Mexico. So he, but anyhow, he's saying no. This is an impact crater. And well, if it's an impact crater, where is the meteorite? It must be buried down here. And so there were miners. There were iron miners who bought the land so they could get this huge meteor that they were sure was just sitting down there that they could mine for its natural resource. They could not find the meteor. That's because it hit at high speed velocity. It was a high velocity impact, which means its collision energy was greater than the binding energy even of the iron atoms itself. And 90% of that thing vaporized on impact.
Wow. My brain
There it is.
like
There it
this.
is. There it is.
Wow.
There's
That
no
looks
iron.
more impressive even than I remember it.
Okay, the pieces. That's nice low-angle shot, so you get the shadows of the rim.
That's in Arizona. Where in Arizona?
It's near Winslow, Arizona.
Where would that be near? Is that like if
gosh.
someone wanted to fly in to see that?
Here it is. If you go to the Grand Canyon, then you drive to this, and it's a couple hours, 2 hours. Okay, there's Meteor
I might
Crater.
have
The
to
map is
go.
coming up. And where's the Grand Canyon? There's Meteor Crater and Grand Canyon, which is also in Arizona.
Flagstaff.
Grand Canyon National Park. You can drive that. See that Grand Canyon to Meteor Crater through Flagstaff? Yeah. So you're not going to fly that. You just drive it. And
It has Yelp reviews.
It's a
Look at that. Look at that. Look at it highlighted. It's got 5
you can't
stars.
Yelp review
Look at
a
it.
crater.
Look at it. Look
Come
at
on,
it.
no.
Look.
Why doesn't it have all the stars?
Look. I know it should have every goddamn star ever.
No!
Only 3.9.
It's
People
a
are so
freaking meteor
picky.
crater.
It's not that big a deal, man. I can dig a hole better myself.
Oh, by the way, so this hole was this meteor crater was dug in like, a few seconds. This crater was made.
Yeah.
Just
And how many years ago was that?
50,000 years ago.
That's nothing.
Approximately nothing. It's
Wow.
nothing.
There's probably some form of human living here then.
Oh yeah, early humans.
Maybe.
I don't know if they were in North America yet.
They say 40,000 is the most recent, right? Isn't it
Yeah,
most-
it's just when they crossed the Bering Strait.
Yeah.
That's when they would have just arrived.
Man.
They would say, "Oh, that's cool. I'm going back."
Have you gone? Have you gone to that?
Oh yeah, multiple times. Oh yeah.
Is it freaky?
What's freaky about it is you walk up to it, you can't see it because the rim of the crater, it just looks like a ridge line.
Ah.
The rim is raised above the plane of the area, right? Because when you press down, it raises it up a bit. So you just walk up to it, and then you come up to the ledge, and there's like,
You realize what it is.
this is nearly a mile diameter hole in the ground. Oh yeah, it's a stunning encounter with the forces of nature.
And the fact that there's so many of those particles just floating around out there. They
Oh
can
yeah,
easily
that was
just
nothing.
slam right
That was
in.
nothing. That's.
How big was that one, you think?
Oh yeah, that was about about I don't know 20 yards across, something like that. Yeah, that's nothing.
That's nothing.
That's nothing.
That's it? 20 yards?
Yeah, but maybe between 20 and 40 yards.
20 yards is the size of this
Oh yeah,
building.
that's right.
From that garage to that front door
Yeah,
is
now make that
exactly
kind of
19
circle.
yards.
Yeah.
Wow. That's crazy.
Right. That's not, and that's the kind of thing that can get close enough that you don't even see, and then it's too late.
And
Now,
those
of course, that's
things
not going to
do
render you
sneak in.
extinct. That's not going to make us extinct, but it'll
But-
make a very bad day for a city.
Yeah.
Okay.
Yeah, the city's done, and
Yeah.
most likely the power grid's jacked for a long time too.
Right.
Now,
What
I
time is
wanted
that? Is my
10 till.
plane left
10
yet?
till. No, you have 10 more minutes.
Okay.
So I had to get the Stephen Hawking's quote out for you. Stephen Hawking's was talking about the possibility.